warm welcome to Damian.
Thank you so much, Turtle. It's always fun to be back here. So yes, that works. I'm Damian. I am a freelance consultant, CTO, and also software trainer with my own company called Stack Mechanics. You can find me around at most places under something Damian M related. Not Twitter so much because that's dead. I play guitar, I make coffees, I ride bikes, I do stuff. I don't just do microservices. So, and firstly, a couple of thank yous. So firstly, thank you to .NET Meetup, thank you to Telstra. Also have to thank JetBrains. We have 2 free personal subscriptions to JetBrains tools for the best question/heckle of the night. So save up those questions, I can take it. Also want to thank Loren for doing my slides. Anyone who's worked with me knows that I'm not the most visually artistic person. My whiteboard drawings are a bit notorious. So Loren, thank you. Helping me with so many animations. This is the most animated slide deck that I've ever had, so thank you. Sorry?
Did Tilly help too?
Tilly did not help. Yes, last time I was here, my daughter came up and gave a talk, but she decided to stay home tonight. But that's on YouTube. Anyway, agenda for tonight. So I'm going to give a little bit of background to sort of what this talk is about and why it exists. I'm going to talk about why I like to use messaging, some of the places that I've found it works really, really well. I'm going to talk about sort of messaging concepts from like really sort of beginner, sort of first principles of messaging right through to some sort of advanced scenarios and modeling. Really, this talk is largely about how to model your distributed applications using messaging. So yeah, going to get into sort of some common architecture patterns, talk about how to deal with failure, because in distributed systems, you always have failure. I've had 2 conversations about Azure in the last 5 minutes, so they know all about failure. And then a couple of other sort of practical considerations around building this stuff. Cool. With me? Take a breath. So a bit of an introduction. I've been doing messaging async distributed type applications now for a while. 2009, I think, I first started working with Service Bus and MSMQ, so a while ago. And, you know, not the solution for everything, but, you know, had a lot of success with messaging architectures and, you know, ended up building training courses around it because I've sort of see people do microservices wrong, and I've sort of, you know, been around, do a lot of architecture, do a lot of helping companies sort of dig their way out of holes and stuff like that. So that's sort of what this talk is, sort of, yeah, is stuff I do anyway. But a few months ago, Brendan Richards came and gave a talk on Azure Service Bus here, and I think at the Azure user group. Did anyone see that? A couple of you? Yeah. So a really good talk. And it really sort of covered some of the sort of basics of Azure Service Bus really, really nicely, and that's great. Like, I love seeing people get out and talk about messaging. And over the last few years at conferences like YOW, people have sort of talking about async design as a way to, you know, get lower latency, better fault tolerance, better scaling type stuff. But it's one of those things that I find, particularly with clients that I work with, it's like, yes, we would like to do messaging, it's hard. So you can go and look at the documentation for, say, Azure Service Bus, and it'll go download the SDK, and then create a connection here, and then create a, you know, connect to this queue or subscribe to this message, and then just kind of sit there in a spin until a message comes off and then run some code. And that's all well and good, but it's not really, you know, how to build an application. It's like saying, here's how to write a select statement. Use an ORM. Like, it's kind of like it's a jump between the sort of 101 hello world documentation and actually building applications. So yeah, tonight I sort of want to share some of the concepts and patterns that I've used over the years, that I've taught over the years, and I've had success with over the years. So that's a bit of an intro. So really we can thank Brendan Richards for me doing this. So that's a great talk. I'd love to give the second part to that. Cool. So, why messaging? Now, who's seen me speak before? Occasionally I get a little controversial. I'm going to try not to tonight, except for this slide. Oh, not this one. This one. The problem with synchronous calls in microservices. It makes your pet elephant sad. Microservices became this big thing a few years ago. And everyone went, cool, microservices, and they all started building up. And I've given a whole talk about this several times. A bunch of you have probably seen it. But people spun up a whole bunch of services that started to talk to each other with HTTP. And I've seen very, very few of those things actually get to production. I've ended up rescuing a lot of those things. And the ones that do sort of limp into production have lots of problems because we end up with this kind of synchronous chain of calls. And when we do kind of synchronous distributed computing like this, we introduce a whole bunch of failure, and chains of failure. And so our deployments come really hard because, you can't deploy one thing if it's in the wrong order because everything falls over. Failures become multipliers. So it's not just this service failed, it's this service failed and all the way up the chain failed along with it. Latency is a multiplier. Scaling becomes really, 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 really hard. And no amount of, but we use poly will save you from this reality. I knew that one was going to get a laugh. And here's the slightly controversial thing. Relying on this as a pattern in a microservice application will make you lazy. And I'm judging you.
I thought the whole point was that it made scaling easier.
Sorry? No. Well, it doesn't, because if you've got this thing, and you've got lots of them, but they rely on this, which relies on this, and this one goes down, you multiply your failure. It's an ON of failure. Sorry? Oh, the question's for Mike. So the question was, doesn't microservices help scaling? Yes, microservices help scaling. But when they are on a chain of synchronous calls, you multiply all of the latency. Yeah? Microservices good. Putting them all in a chain, bad. Yeah.
So if service A goes down, everything else will go down?
No, the other way around. So if you've got traffic coming into service A, but it's calling, and like the canonical example in every microservices documentation is, you've got your catalog service, which talks to the pricing service, which talks to, if one of those goes down, they're all going to fail. And yes, poly might kind of give you a 404 instead of a 503, whatever. But, your failure multiplies. I can talk about this for hours at a time. And I have, and I will, but that's not the point of this talk. That was the last talk. But yes, I find people jump into this, and the sort of the summary of the other talks I've given is people jump into this because they go, cool, microservices tech, we're going to do all this stuff, Kubernetes, and they forget about modeling their application. and it's because we've kind of got this mentality that we used to have, which is we'll just query that table. And so they just query another service, which queries another service, and all of a sudden you sort of introduce this chain of fail. And it's kind of lazy. I've had a lot of success with something that a few years ago as a joke I called mullet microservices. HTTP at the front, messaging at the back. It generally gets a laugh, so I've stuck with it. I've had a lot of success. It's not, there is no one architecture for everybody, but in a lot of places, this works quite well. So you've got services that can have traffic routed to them. Each service owns a business process, So if you go back to definitions of microservices and go further back to the definitions of SOA, and they're basically the same thing, that's controversial. A service should own something, yeah? And when they own something, you can route traffic to them and they can just do their thing. And that scales quite well. And then where they need to communicate with each other, which is the guts of what I'm getting into tonight, they do this on this kind of messaging backplane. So if this is, a shopping cart service, it knows everything it needs to do, knows everything it needs to know to be a shopping cart. If the product catalog service gets a new product, it'll publish a message out saying, hey, there's a new product to put on the page. So they kind of communicate in this messaging backplane. It scales really well. You can afford to lose service D for a little while. It's not going to affect the other ones because they're not kind of synchronously waiting on each other. And then on the front, obviously, if you're dealing with the web, HTTP, it was designed for it. We've got caching, we've got CDNs, we've got, a whole bunch of infrastructure. Yeah, we still use HTTP at the front.
So service D goes down and the message bus goes
So,
up for a while?
yeah, if it's got messages waiting for it, and I'll jump into that. If it's got messages waiting, it's not going to stop these other things from working. Whereas in this scenario, if service D goes down, everything goes offline because they're all relying on it.
But B and C can still talk, right?
But if the call from A calls to B and says, hey, give me this catalog, and he goes, oh, I need to check the price of that. And there's like every microservice documentation goes, the catalog needs to talk to the pricing service. And it goes to that. And it goes, oh, but hang on, I need to check the region pricing service, and this is down. Then this is going to time out, and this is going to time out, and this is going to time out. So you've got this cascading failure. So yeah, whereas this, you go obviously if service D goes down and you're trying to route requests to it, you're not going to get there, but the rest of your app is going to stay up. So, in a distributed system, I think it was Google that sort of started talking about this concept. When you have thousands of computers, if your computers have a 1 in 1,000 failure rate, you always have a failing computer. So in distributed systems, you have to build around the fact that something is always broken. And breaking away from synchronous calls helps you withstand that broken. So going to an async model helps you withstand that broken, but you need to change your modeling, which is kind of what we're talking about a bit tonight. All right, so that's the mullet. Had a lot of success with that in a lot of different areas, and mullets are funny. I have an 18-year-old who just went, Dad, I want to get a mullet for school. He's just like, I have failed as a parent. He turned 18 this week, and I've just kind of failed. Anyway, so, yeah, and it comes around sort of loose coupling and domain design, right? These are concepts that if we're writing code, we're writing sort of OO code and classes, we understand that our stuff should be loosely coupled and cohesive, and, we understand how to model stuff. And we need to sort of apply those concepts to our service design. Or, if you've got code that has to call every other bit of code, it's kind of, you would look at that in a code review and a PR and go, that's bad code. We need to apply that. So, I sort of got to thinking about, when everything, when all you have is a hammer, everything looks like a nail. If HTTP is your hammer, you start to put nails in some really bad places, which is why I said makes you lazy. So, whereas if you think about the sort of hammers in themselves are not bad. Who has ever kind of done like art or music or writing or something like that? You have exercises where it's like, okay, write some music, but you can only use these 4 notes. Has anyone done an exercise like that? Or you can write, but like you can draw, but only with 3 colors. Like having those constraints kind of makes you think about stuff differently. Yes. White space. Sorry? It was not a serious question. So when we think about messaging, it's really helpful to think in terms of events and commands, because events and commands are about behavior, right? And behavior is how we model rich domains. Yeah, so it sort of makes sense that to kind of model these good domains. If we think in kind of terms of events and commands, it's going to help you model your domain better, right? Now, I did not just say that event sourcing is DDD. I did not say that. It's not. I've had people argue with me about that, and that's not true, and that's not what I just said. I get misquoted a lot. I did not say that. So, right. So with that, I'm going to talk about some basic messaging concepts and building blocks, and then kind of build up to how we put our applications together. All right. Commands. Commands are like really basics of kind of messaging. So who's used commands inside of, their normal code? Command pattern. Yep, cool. So a command is like this one-way message that says, go do this, right? Send an email, generate a PDF, call the payment gateway. It's this kind of very simple thing. It's just like, do this. I'm not even going to wait for a response. Just go do it. That's a really good building block for sort of distributed systems. And then the other one is pub/sub or events. Who's heard of that? Who's used events in kind of OO code? It's good. It says, hey, this thing just happened, right? In messaging, it's a message that you publish out and says, this thing happened. And that could be, a payment succeeded. The command was call the payment gateway. A message says, hey, look, that order succeeded, or we've got a new order, or a customer signed up. Those things are events. And then any service that cares about that type of event can subscribe to it. Say, hey, that thing, I care about that. I would like to be told when that happens, okay? That's one of our basic building blocks. Cool. Now I'm going to get into the next level, which is message brokers and queue topologies. This is where it gets fun. I'm talking too fast. All right, so message brokers or message buses. The terms kind of get wildly interchanged. So I'm going to say broker and bus interchangeably. They mean basically the same thing for the purposes of this. Essentially, it's a piece of infrastructure that handles like the routing and delivery of messages. Okay, and it's really good. Like you can think about it in terms of post offices or mail servers and stuff like that. A mail server is basically a message bus, message broker. But some examples. The one that everyone felt the pain with last week was Azure Service Bus. It's usually pretty good. RabbitMQ, ActiveMQ, there's a bunch of them. Who's worked in kind of messaging systems? Oh, a bunch of people. Who's worked, sorry, put hands up again. Who's worked in them that I haven't worked with? Yeah, there's still a bunch, yeah, cool. Cool, so it's a piece of infrastructure. It's a kind of a server that you install, right, or subscribe to. And most messaging infrastructure, they all have their own quirks and idiosyncrasies and slightly different features, but most of them have kind of two like primitives, which is queues, and then topics, exchanges. There's a few different terms that basically mean the same thing. So they're kind of our two building blocks in messaging infrastructure. Okay, queues are a pretty simple concept. Like again, we've got that just in code, like there's a queue data structure in C#. It's just a data structure essentially that you can put a message on and you can pop it off the end, yeah? And so in like message bus land, it's a pretty simple pipe, and you can go to AWS and you can use simple queue service. It's pretty simple. You just drop a message off and then something on the other end can say, give me any messages as they come. Make sense? All good? Feel free to like, if I'm losing you, put your hand up, please. I like being interrupted. And then we've got the more advanced one, which is topics or exchanges. And again, I'm going to use these sort of interchangeably. And this is where the sort of pub/sub comes in. So basically, we've got something that's creating these messages and it's publishing them. And the broker then makes a copy of those messages for everyone that's interested in them. So in this point, we've got two types of messages. We've got our yellow ones and our pink ones, and they get pushed into the broker. And then over here, we've got our subscribers. And these two care about topic B, and this one cares about topic A. So the message broker will get that message and goes, well, I know you care about A, so you get a copy of A, and you too care about B, so you both get copies of B, and they both get their own copies of it. Much like being on an email list. Yeah? Who's on an email list? Yeah? So if I'm sending a message to a list, I don't need to know the email addresses of everyone, until they put everyone in CC, but I can just send a message to that list, and any subscriber to that list gets their own copy in their own inbox. So one person can read it and delete it, and it can still be sitting there unread in someone else's inbox. Message exchanges in pub/sub work exactly the same way. It's even called Exchange. So that's how that works. So, and I think for there, like most people are pretty comfortable with that. Like, who is this new to? A couple of people? Yeah, cool. A little bit? Yeah, cool. If you've played around with sort of messaging infrastructure and Azure Service Bus, queues and topics and exchanges are pretty close. They're like, this isn't.
Sorry, what about like shared inboxes
from an end user perspective? There is an analogy for that. Bear with me, but we will kind of get to that. So the question was, what about shared inboxes? And yeah, any analogy can get stretched and torn in a weird way, but actually, I can come back to that one. Because that's, I'm getting to that. So far that's kind of basic. Like if you've kind of read the documentation for Azure Service Bus, you will have understood this. There are queues, there are topics, and there are subscribers. Yes?
Is this from like one email address to another? Because I think I can.
Let me back up from the whole email server thing. Like it was an analogy that had its time and place. Let's come back to messaging infrastructure, because otherwise we're like, but what if I'm BCC'd? I know. Yeah, analogies only work so far. Metaphors. Yeah, but we'll probably answer your question anyway. If at the end you haven't, hit me with a question. All right, that's sort of fairly top-level documentation stuff. And again, this is stuff that you can read the documentation and go, cool, how am I meant to use it? One of the really big things that I think gets missed is you can do a lot with naming conventions. And a lot of what I found makes this stuff really simple is just understanding what things are called. So in any one of these sort of pieces of infrastructure, queues have names, topics have names, and if you subscribe to a topic, that subscription generally gets a name, right? And they can be completely random names if you want, but that's not going to help anybody. If you're sick and the next developer comes in and go, what's this queue called Elmer Fudd about? No one's going to know. So good naming is important in any engineering discipline.
I joined a company and it was called Rabbit, and I thought, Googled that.
And that's not probably appropriate for this meetup.
People were in costumes.
This is a family-friendly event, Jules. Anyway, so what I found success with is you can name your stuff after things like the message type or the application that's either sending it or listening to it. You can have application instances in the names, the actual function that handles the message in the name to model stuff. So basically with a good naming convention, you can then you can model a lot of behavior inside your messaging infrastructure through good names. And I can see I've just lost a few people, but bear with me, I'm bringing it back. Yes.
This is probably a bit off topic, but can that also mean, in this case, just using basic acronyms with basic prefixes at the beginning of your...
I've got some examples, so I've got some examples. It will make sense in a moment. Good naming though, it's again, good engineering discipline. So here's a good example, command queues, okay? So we've got a command that says, I would like you to generate a PDF. Now I would call that queue something like queue, reporting service generate PDF command, okay? That makes sense because then I can, in my code that has to subscribe to that, I can say, I want to generate a PDF. I can write some infrastructure to automatically wire myself up and go and find that queue that says, I would like to handle this message type, therefore I will go and connect to the queue that is of that message type. So I've kind of used the service name, either the publishing one or the consuming, small detail there that we probably won't get into, and the command name to say, here's this thing. And what we can do with that, once we've got a good naming convention in our architecture, I don't need to worry about all of the people working with me. I can just say, if these queues are going to be named after the type of message that I'm publishing them, then an application can say, hey, I would like to subscribe to that message because I would like to handle it. And through that convention, I can wire it up, and it works. So in this instance, we've got a reporting service that generates a PDF, and it knows that it wants to do that, and it knows the message type that it wants, so it can go and connect to that queue and subscribe to it. And it will just sit there polling that queue. So basically, all the clients work slightly differently, but essentially they're sitting there, they make a connection to it, and they'll just wait for a message to pop up. And a message gets put on the queue, sits in the queue, this thing will poll, pull a message off the queue, generate its PDF. Good so far? Yep.
Yeah.
Where this gets really fun is we essentially get scaling for free. Like load balance scaling we get for free. Because we know that we're going to connect to this queue, we can spin up multiple instances of these things. And because they're all polling the same queue, it becomes this kind of round robin scale out. So scaling becomes very, very easy in this because we just add it. And here's an example. Yep.
So I have a question.
Yep.
These are different instances of the same subscriber.
Yep. Yep.
Subscriber is one over here.
Yep.
Instances.
Yep.
Different subscribers, right?
Yes.
Okay.
I will come to that. This is a very simple example where we've got our generate a PDF, but I'm like, actually our PDF generation has gotten really slow. We'd like to scale that up. So what I can do is I can have lots of instances all hitting the same queue, and ready? You get one, you get one, you get one. Animation. First time I've ever had animation in a slide. Handful of red, please. Okay, so just by spinning up more instances and connecting them to that same named queue based on our convention, we kind of get automated scaling, load balancing, scale out. We can tear them down. Again, this is one of those things that doing point-to-point HTTP from the sort of origin gets really, really hard because you've got to spin something up, you've got to connect it to the load balance, you've got to warm it up. It's kind of painful. This thing is like a pull model. Pull models work really, really well in something like this. So we kind of get this kind of scaling for free, which is nice. I like getting stuff for free. All right, events. Our events are a little bit more complex, okay? So events are, and I think this is a question that you're asking, which is, we might have multiple things that care about this event. So this queue model doesn't quite work. That's a very one-way pipe. So with events, we might have an order service that publishes there's a new order event. It's got some metadata in there. Now here, it's gonna hit this topic, and that topic might be called T for topic, order service, because that's where it's coming from, order service messages, that's the namespace of the message, new order event. So it's kind of named after the service and the message namespace. And then over here, animation. We've got these two different, completely different services that care about this type of message, yeah? I can hand out slides after as well, if you'd like. It's up to you. I take photos as well, because I lose PDFs. But I can publish them if you like. Sorry? So yeah, we've published it to this topic. Again, topics, exchanges, roughly the same thing. Azure Service Bus calls them topics. RabbitMQ calls them exchanges. It's basically the same concept. Over here, we've got these two different services. We've got a warehouse service that cares about that because it needs to, pack up an order. And we've got a report service that keeps a track of some totals. Now, they obviously both need a copy of that message. Yeah? If it was a single queue and the warehouse service got to it first, it would pull that message off and then the reporting service wouldn't know about it. Okay, so that's where this pub sub model comes in, where we publish it once into the topic or exchange, and then each of the subscribers says, hey, I want that. And this is where the naming stuff starts to come in. So commands were super easy, even to scale it. This one's going to get a little funkier. So here we've got a subscription. So here I've named the subscription after the subscribing service and the message type. We can go deeper, but I'm trying to keep it here. So basically, there's a subscription that says warehouse service new order event, and we've got another subscription called report service new order event. Now, because in my infrastructure, in my architecture, I've got a naming convention, I don't need to manually configure these services to talk to that. They kind of do it based on convention, which is important, and I will come back to this a few times. Again, the Azure outage last week was one instance where a very old service bus was going very, very slow, and the application would have needed to be reconfigured to pull it down because everything was hard-coded, like exactly for that queue name, and it was a mess. So yeah, we've got subscriptions and they're named after the service that's subscribing to them, okay? So what happens here, we've got the new order event comes in, they both get a copy of it. And they both get a copy of the next one, and they both get a copy of the next one, and then they're done. Woohoo! So they all got their own ones. Yeah? Yep.
Before we move on to the next slide.
Yep.
Pink thing there is the topic.
Yes.
It was subscribed. The blue thing is the queue.
Yes. Yes. Yeah. Yeah. So yeah. Yeah. So this is I've just called them different. Yeah. So this is the topic. So the one of the great ways. Problem with animations is going back is really hard. Although then we get to see it again. One of the great things about this is, with a pub subsystem, is this service doesn't need to know who is subscribing to it. It just says, hey, this thing that I find interesting just happened. If anyone else finds it interesting, cool. But like, it's not on me to tell you. If you're doing more of a point-to-point thing, you'd have code that says, okay, we've got a new order, we need to tell the warehouse service. And then somebody spins up a reporting data warehouse thing, and then they've got to go to the team that does the order service and say, hey, can you call us as well? And so then that's a code change, which kind of, going back to our good domain modeling, who's heard of like single responsibility principle? Yeah? So we don't want to have to like go and extend a class every time, someone else is interested. So this kind of fits with that quite nicely because we're saying, hey, this is an event, this happened, and then, you can, I'm going to use scale in a different way. You can scale out your whole like dev team. You can have a whole other team building a data warehouse reporting system. They don't have to bother everyone else. They can just say, hey, I care about that event and that event and that event and that event, and I'm going to collect that data. So it's kind of really follows like the open close principle really well. So we can kind of just extend our bigger application by subscribing to events. And now we can see the animations again. Woohoo. So exciting. Yep.
So if, for example, you get an order, but then you need to do a prerequisite, say we need to do a credit check.
Yep.
Can you put that as a command before it gets
So let me come back to that. So the question was, if you've got an order but you need to do a credit check, there's a pattern that solves that exact problem. And I think I even talk about orders. So yes, but I will get to that. It's called a saga pattern. Okay, so that's our event handler, and that's kind of worked really well. We can then, again, scale's a very loaded term at this point, but we can widen our application without interrupting anyone else, because we can just say, hey, I care about that event, and each application that cares will get its own copy of it. All right, now we start getting fun. So that last one was just event handlers, okay? Pub sub event handlers. Now we're talking about competing event handlers. So this is where, again, this is where we can get some of our scale for free if we follow good modeling conventions and naming conventions. So in this example, we've got an upload service that uploads, a piece of data that needs to be processed. So it publishes this message. It says, hey, look, I've got a new piece of uploaded data that needs to be processed. And in this case, I've got a processing service that will subscribe to that. Now, at this point, this processing is slow, so we know that we want a couple of these things. We've got quite a short SLA on processing them, and it's quite intensive. So we can scale this out, which in most sort of container orchestrations, you just go into it and either in your Terraform or your GitOps or whatever, or go into the and we can scale them out quite easily. And
Hang on, why is there two queues?
sorry, why are there two queues? So we've got our topic, which is this is where it's getting published to. Yep. We have one subscription queue. Okay. So we've got multiple services hitting the same subscription name. Yeah? So before we had two completely different applications. So they hit two completely different subscription names. Okay? But a subscription has a unique name. So in this instance, we've got two copies of the same service, but with the same subscription name. So this is like our competing command handler. So this will then round robin. See? Ready? Okay, so we've scaled out our event handlers because we've got event handlers that are competing for events. So again, because we've had our subscriptions named well, we've modeled multiple services with the same subscription name. Okay, we'll then scale out. Ready for the next level? Multicast event handlers. Now we're getting fun. So this is where we've got, there are instances where you want multiple instances of the same application type handling the message. Okay, really good example is a cache. Okay, say we've got a big e-commerce site and we've got a service that shows, catalog bestsellers, something like that. We don't want them on a shared database. We want to distribute them around in shards or whatever. So we might have multiple services that each have their own like Redis instance or something as a data store. When a new item comes up, we want to make sure that every one of those instances gets it so that our caches kind of stay in sync, which is not the, here I've just gone with a generic name. So we've got a service, it publishes an event. Again, its topic is, a service messages some event. Over here, we have two instances of the same service. Yes? Now before we had two instances of the same service, but we wanted them to compete for the event so that only one of them handled it. In this case, we want every instance to get it. And keeping local caches is a really good example of that. So in this instance, their subscriptions are named differently. They're like some service instance A, some event, and some service instance B, some event. So in this point, when they've connected to the message broker and said, I want to care about this message, they've given different subscription names. Okay? So they will both get messages.
Can you get more literal on the cache thing?
More literal?
Yeah.
Cache is a really good one.
So this is the catalog, right?
Yep.
So we've got what? Let's say one in Australia and one in Singapore?
Yep,
Like
sure.
the
It could be geographically distributed, or it could just be just for redundancy. Like this thing's getting slammed, and we want to make sure that each one of them has its own cache in Redis or in memory or whatever. So like,
Where's Redis?
it's a database. Work with me, Jules.
Okay.
So, but what we're saying is, in before, we were like, we've got multiple instances of the same service doing the same job, but only one of them wants to do it. A really good example is that, you only want one service to create an invoice. You don't want each service to create an invoice. But if it was each service needs to know the new products or the best sellers or whatever, then you want to make sure that each of them gets that. And they get there through naming conventions of their subscriptions. And again, with a convention, you can wire it up. You can configure it in code. Make sure this is multicast. And it will add its instance ID into the subscription. Yep.
So both instances here will get all the messages, right?
In this instance, yes, that's right. Yep. Yep. So they get all the messages. Oh,
I just
yes.
I just
Yep.
switch it back
Oh,
on
you
here.
turn it on. Yeah, that'll work.
Yep. Where do you want that? Just like there.
All right.
And then you can put your lectern however you want it. Yeah. Is that cool? Yeah.
Cool. I'm back.
Batteries don't last forever.
Batteries do not last forever. A good example of failure in distributed systems. See what I did there? So yeah, sorry, I was saying, yeah. So machine name is a really good way of making an instance unique. But yes, in a very fluent cloud environment, instance names can be very random. There's a couple of going sort of beyond the scope of this talk. There's two problems you've got. One is you need to clean up old subscriptions because they'll just, yeah, so you need something to go and prune old subscriptions. The other thing you need to care about is if I spin up, particularly in the cache instance, you kind of need to worry about new one spins up. So say you're on like, spot pricing on AWS or something, new one spins up. You need to make sure that you've kind of bootstrapped your data set before you start accepting messages. And that sort of gets a little bit tricky. But yeah, that's kind of way deep at that point. Does that answer your question? Yep, cool. Sorry, did I fully answer your question before? Yep, awesome. Okay, so that's our multicast event handlers. Now you can mix and match those too. You can say, of this one message, the warehouse service needs to get it, but only process it once. The cache service gets it, but make sure everyone gets a copy. So you can kind of mix and match that. And again, it's through these subscription names. So if two services are sharing a subscription name, they'll share the messages. If two services have unique subscription names, they'll both get a copy. Yeah? And animation. All right. So that's kind of how we handle the different layouts through naming conventions. Before I move on, did I lose anybody? Nope. Cool. Are you just being polite? Yes? All right. Distributed application patterns. So what this is about is again coming from the monolithic app where it was easy to just call another class, cross a namespace boundary, query SQL, run someone else's stored proc, join a table. That was easy. As we distribute out, those things get harder, and trying to replicate those things exactly is how we kind of get our synchronous chain of mess, right? So moving to this kind of asynchronous distributed world, there are a bunch of patterns that kind of take those places. And I can't get anywhere near as animated as I want to be now. So here's just some of those patterns that will come up. So the first one is, it's known as system of record, and it's basically like in a sort of microservices architecture, distributed system, a piece of data has to have one owner. Yep. Now, it doesn't need to be like everything about a customer, but it's, because services should own like a business process or something. So in this instance, we've got a customer service and a loyalty service. The customer service owns the details about the customer, but the loyalty service might, own their opt-in and opt-out, mail preferences, a copy of the purchase history, that kind of thing. So the customer service owns the master record of the customer, and it can publish events to say we've got a new customer, or the customer updated their address or phone number or email address or whatever, depending on your system, and those things get published as events. And then so other systems can have copies of that data, but they become read-only, non-authoritative caches. So you wouldn't go to the loyalty service to get, like the loyalty service can have a cache of, someone's name, but you don't go querying the loyalty service for that customer's name because they may have changed it and the customer service owns it. Okay, that's a kind of really important one when you're modeling this is for everything, which service owns it and which just has a copy of it for its records. Another good one is, again, in a sort of more monolithic system, you can just join a table. you can't do that really well, or you cannot do it efficiently. So a distributed replacement for joins is something called a materialized view. So essentially, you might have multiple services publish events, and then another service listens to those events from multiple services and kind of flattens it out like a denormalized cache structure. So in this example, we've got, you know, an order service and a rating service into, you know, a sort of hot product service that says, these are the, you know, the products that have sold really well today or highly rated today. Like, this is what people are talking about. And essentially, you know, if you can imagine a table joined, as orders come in, it grabs it, creates a row, or, you know, looks up a row. As ratings come in, it puts that in that row. So we kind of flatten it out in that kind of distributed view. So that's a really good one to kind of get scale without having to go, someone's called the hot product service, we need to call the order service and call the, you know, call these other services under load, where it gets really, really ugly. So like, multiple copies of data is good as long as only one thing owns it, and we can kind of flatten it out and denormalize it. That make sense? Yep.
So, sorry.
Yep.
So, with the cache, you're placing that cache in a local database like SQL Server. Or something.
Absolutely, yeah. So every service wants to have its own database. And this is partly why document databases have come a really long way. Sort of a lot of popularity with these sorts of architectures, because you don't care about like the one true like normalized schema. It's like, I'm just going to have a bunch of blobs, but you know, you can get a blob out of, you know, Mongo or even Postgres. I use Postgres for pretty much everything actually. So yeah.
So you use pretty much any like NoSQL sort of databases when it comes to basic caches. And
For a lot of stuff, yeah,
right.
yeah. Actually, I tend to, my go-to now is Postgres, because it does relational database exceptionally well, but it's also an excellent JSON store, and it will index on JSON, and I can talk all day about that, but that's sort of, sorry, next month's talk, yeah, Postgres and Martin. Sign me up. But yeah, it's sort of like, in the old days, it was like you could have one copy of every, like normalization, like third, like one copy, only the key, chars, because varchars were inefficient. You're like, yeah, I just got the old people. I saw you laughing. Yeah, whereas this works really well because like, you don't need a perfectly normalized schema for stuff like this. So like, documents work really, really well. They're fast to retrieve, you know. It's sort of, we can mix and match our sort of storage techniques a little bit. Cool. Another really good pattern, I just call it like a packing slip. So it's, again, to avoid having to call into a bunch of services. Like if you're sending a shipping manifest to a warehouse, like go and pick up 5 copies of this book, here's a reference number. You don't need to know the person's address. You don't need to know their billing details or whatever. Just like, here's the thing you need. Like, when you order food at a restaurant, you know, they don't need to know your name or your credit card number or whatever. It's just table 13 wants some fish and chips and a burger. It's just like this slip. And then when it comes back up, and I'm jumping ahead, there's an order ready for table 13 and somebody will come and get it to you. So that's a sort of pattern that works really well, is like, put the information into a message that another service would need to know. All right. Transactions.
So, Dave,
Yes.
I'm going to expand on, do you mean routing slip as well when you say packing slip?
No, not a routing slip. No, that's a little bit different. Yeah, a routing slip will go, do this and then send it on. Yeah, that's more like a distributed saga. No, this is more around like putting the metadata into a message so that the thing that receives it has everything that they need. They don't need to go and do a bunch of lookups. Again, it's like redundant data is okay. Yeah, routing slip has a little bit more logic into it. All right, so the next one is, the next kind of thing that we used to fall back on is transactions. And I can't say it better than Pat Helland, which is grown-ups don't use distributed transactions. You know, in these sorts of architectures, trying to do anything transactionally is bound to fail. You can't unsend an email. Is another good example of a distributed transaction that does not work. And I've seen people try. I've seen people it's like, this call to a third-party loyalty system failed, roll back the order. It doesn't work. You cannot do it. They unfortunately went in thinking that, yes, they could make this system transactional, not realizing that their network infrastructure was overloaded and 25% of all of their external calls failed. Few people in this room are on that project. And we laugh about it to this very day. Okay, so distributed transactions do not work in this kind of environment. So we've got to have other patterns. And I think this answers the question that you had before, which is something called a saga. So a saga is essentially, usually one service will own a saga, but it's basically owning the status of a business process. Okay? Sagas at their heart are just a state machine. So who understands state machines? Yeah, most of everyone. So state machines is this sort of, I guess, pattern that says that owns the status of a process. Okay, and you can tell the state machine things that have happened, and it will figure out what's next. Yeah. So in this instance, you've got a service that holds the status of a long-running kind of business process, and it can subscribe to the events relating to that business process. And then understand for that particular instance of that business process, where's it at? So I think the example was if you've got an order, but you need to do a credit check first. Okay, so an order would have a couple of statuses, and I think I even have that on my next slide. We've got a new order. So this saga process listens to that and goes, okay, we've got a new order. Its ID is 1, 2, 3. I'll kind of store that away. And then we've got an event comes in and says, payment was successful for order 1, 2, 3. And so the saga service will go, order 1, 2, 3. I know about that one. Pull up its kind of status out of the database and go, cool. It was a new order, so it's kind of in this pending state. We've had a payment successful. Cool. Its status is now paid for. And then later on, the warehouse says, hey, look, we've packed that order. And then you can go, cool, this has happened, this has happened, this has happened, tick, 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 ship it. Yeah? So that's how we get around this knowing when something can happen. So this saga pattern can go, and it might be the ship the order might be a command. So it's like, okay, the payment successful, because sometimes these will come in out of order, like the warehouse might have packed it before the payments happened. Because payment gateways are notoriously reliable, aren't they? So they may come in different order. So when any of those orders come in, you'll kind of open up that file and go, okay, it's been paid for, the warehouse has got it, cool, now we can send it off. Yeah? And this is another really good one around we used to, thinking about transactions, one is, well, we need to wait for the payment to come back in. Now, who's worked with waiting for a payment gateway? How consistent are they? Not very, right? So it might, so rather than a synchronous HTTP handler going, call the payment gateway and wait, and we've got a 30-second timeout, but it takes 32 seconds, it's not going to work. So instead, you fire out a command to the payment gateway and say, hey, look, process this, and have a webhook interface for when it succeeds. The webhook gets hit, and you go, cool, send the message, the saga will pick that up and go, cool, this payment was successful. Because sometimes they're not successful. Sometimes the card's expired, it's declined, insufficient funds or whatever. And then you've got to figure out what's the business process that's next. Okay? Because transactions don't work all the time. Business processes are not successful all of the time. The happy path is very rarely trodden. So you might have an order, you might attempt to make the payment, and it comes back with a payment declined. So then what you've got to do, this saga pattern then has to go, well, now I need to email the customer, say, your payment's been declined, come back in, give us a new payment method, update your expiry date, whatever it is, so that we can go try again. Yeah? So that's the job of the saga, because trying to do that in one big distributed transaction and handle all the compounding outcomes of all of those different distributed calls will not give you a reliable system. So instead you have events that come off stuff, and this state machine called a saga pattern that listens to those events and decides what it is. And again, that can be time-based. So you can have a service that goes every night, look at all the orders that have been sitting in pending or payment decline for more than 72 hours, send a reminder email or cancel it or do a refund, or whatever it is that your business process has, you can kind of have these like time-based SLAs on the sagas. So sagas is one of those things that people talk about as this really kind of scary, complex topic, but it's basically just a state machine that listens to all the events and has some checklists and figures out what needs to happen next. Does that make sense? Yeah, cool.
Just had a question.
Yep.
Is a state machine like static? Because I haven't really gotten into that.
Generally, so the question was, is a state machine static? Do you mean like static variables in your process?
Like
Or
there's no real variables. Like it's more like properties.
in terms of actually coding it, or generally what I'll do is, so you're going to have messages that come in on a topic, and you're going to have a message handler that goes, there's a payment successful message come in, and you can look at it and go, it's ID 1234. Now you're going to want to look in your database to go, here's all these transactions, sagas that I'm tracking. One of them has this ID, I'll pull it out, I'll look at all the things that happen. Now you would probably wrap that in a class or some service pattern or something, so you can kind of pull it out and it'll get all the data, look at it all, and then figure out what the state of it is. That would be code, unless it's not, like unless you've got some completely configurable workflow, and then it's got to load up the thing, load the workflow, run the events. So yeah, there's no kind of hard and fast around that. It's one of those things that people don't think to apply because they think it only works if it's really complex. But a saga can be as simple as a row that has, a status and an ID and, some descriptor. Like it can just be a read the thing, it's pending, cool, it's been paid for, it's done now. I've used it for tracking processing of like medical diagnostic data so that you could have an operations person just go, are the things that are coming succeeding or failing? And like literally they had a service with an API that they could call that goes, like with all of the sort of PII and like gory detail of it, it was like upload ID, this came in and it succeeded. Or upload ID, this came in and it failed for X reason, like we might need to fix our validator. Or everything that's come in is sitting in pending because the processing service has fallen over. So that's a kind of simple instance of a saga rather than trying to lock the whole world in a transaction. So I'll get to you. Does that make sense? Yep. Cool. Question?
To risk delving into gory details, do you tend to store the state transitions and like as your messages come in, store
It
state as you transition to it, or only the latest state?
It depends on how complex the process is. So the question was, do I store the states like an event sourcing kind of thing, or do I just, it depends on the process. Sometimes it matters, often it doesn't. There are, no real sort of hard and fast rules around that.
Question from the screen.
Yeah.
What about the cost of loading state to process the saga to the next state, and how to deal with two concurrent events for the same saga?
Cool. So the question was how to deal with the cost of loading that state and how to deal with concurrency. Cool. So they're good ones. So everything has a cost. So the cost of a message has come in, loaded out of the database, look at it, decide on it. Yes, that has a cost. Compared to trying to do a distributed transaction across your 30 services and the payment gateway, it's a pretty low one. Everything in engineering is a trade-off, right? So if you've got that and you've got a nice index on the identifier field, it shouldn't be that much. It's probably going to be baked into some other service anyway, so it's, everything has a cost. It's a, it's a fairly small one. Concurrency is an interesting one. The way, like unless we're talking about Google scale where you have other problems, a really good way of doing it is, again, using that competing event thing where you're pulling events off. Sorry? So, no, but in this case, competing events. So you might have like as a simple way of dealing with concurrency, you only have one service deal with handling that state at a time or for that thing, and you can put, you know, some locks and semaphores and stuff in your code. It's a hard one to answer completely generally.
A local transaction is fine.
Yes. Yeah. Sorry. Yeah. Local transaction is fine. I'm talking about So absolutely, you could have a handler that pulls it out, creates a database transaction, writes to it, and then closes it. Absolutely. I'm talking about distributed transactions do not work. You had another question though?
I didn't. I was going to ask. Maybe I misunderstood the saga, but so I thought what you were saying the saga was like it's holding the state of an instance of a state machine.
Yep.
It's controlling the state transitions.
Yep.
In a single place.
Yep.
So I thought if you had two simultaneous events that it's processing, that it would transactionally apply. Like one would get there.
Yeah.
And it may not do anything other than one because it's not able to transition a state from the second.
Yeah. So if you've got one service handling two different types of messages, then you can do some locking and database transactions around that.
Raise conditions.
Yeah.
Transactionally.
Yes. Yep. Sorry, was that continue? Yeah. Yes. So you don't want race conditions.
No, I was trying to confirm that
Yeah.
you wouldn't get a raise condition because the saga is handling that
Transactionally, that's right. Yes. So yes, if you need to worry about concurrency, the bit of code that pulls the message off and decides the state transition, yes, you would lock that in a database transaction, or put some locks in your threads and stuff like that. Yeah. That's about all the gory details of that one. Cool. Where are we next? Cool. Competing consumers, and I've kind of talked about this a couple of times now, is if you've got kind of really long-running, resource-intensive tasks, you put them on a queue and you have multiple instances reading from the same queue. And it's like, a cheaper alternative to a load balancer for scaling it out. So I've kind of talked about that. The reason I put it here at the end is when they're done, they can raise an event to say this job is done, which completes a saga. So a really good example is, we've got an upload that needs to be processed. A whole manner of things can go wrong in processing that piece of data. So you would have a saga that, I alluded to this a minute ago, you would have a saga that when we got the new upload event would kind of keep a track of it and go, it's pending. Yeah. And then when this processing thing is done, which is kind of, computationally expensive and slow, it's raising an event to say, hey, I've processed this bit of data successfully. And our saga can get hold of that. So had talked about competing consumers as a pattern before, but adding back on, when they're done, raise the event. Say this thing's done now, and then you can email someone and say, hey, look, your job is done. All right. How are we for time? When did we start?
We started at 6.
Started at 6? Oh God, I've got a long time. And I thought I was going to run out of content. I'll try to be quicker. All right, so failure. You're always going to have it. We need to deal with it. I'll move through this relatively quickly. It's just some concepts, okay? One of the things with messaging is transient failures we kind of get for free. And I have put quotes around that because nothing is free. But basically, if you pull a message off a queue and you try to do something to it and it blows up because, some intermittent glitch in the matrix, you can just put it back on the queue and pick it up again later. Yeah? Much easier than dealing with poly and stuff like that. Now, that's not going to work forever. We're going to get to that. But kind of, transient failures work really well. Like if something's just, and I've integrated with stuff that would just like flake out for 30 seconds and then come back. Really good because you go, I couldn't call that service. I'll just wait and I'll put it back on the queue. So free is a joke. It's not really free. Nothing's free. But it's a pretty low maintenance way of doing it. Except, animation. Let's do that again. Ready? It blows up. Put it back on. I did that one all by myself.
Is that why it's lower quality?
Yeah, that's right. Yeah, you can tell.
So, to be honest, is this time to mention the difference between an event broker and event sourcing streaming?
And event streaming and RabbitMQ.
Kafka versus RabbitMQ.
Yeah, no, let's not go there today.
Did you throw that back on the front of the queue?
So I mean, that's the easiest way is, yeah, and I did, the animation's bad. See, I did that one. It should have gone to the end of the queue. Yeah, it should have gone to the end of the queue, because queue's U in queue. Different message brokers handle it slightly different. Some of them, like you pop it off and then you just go, oh, nope, and you put it back at the head. Implementation details.
Claim it, and then when you fail, it just still sits there, right?
Bear with me, I am coming to the solution to that. This is the simple example. Now, the reality is we might want to delay that, okay? So if we've got something that is intermittently failing, we don't want to just pop it straight back on because we're going to get the same failure, okay? So you want to delay it. Now, some brokers will let you do a delay send. You can say, I want to put this back on the queue, but not for amount of time. Sometimes, yeah, depending on the infrastructure, you might want to hold that in memory and go, I'm going to re-queue that in a minute. And again, depending on the infrastructure, whether it goes on the head or it goes on the back, you're like, this message blew up. I'm going to wait again until I try it. There's a bunch of gory implementation, and it does change across infrastructure. So one of the things you might want to look at is like an exponential backoff strategy. So you could say, I've handled this message twice. It's failed both times. I won't put it straight back on. I'll wait 30 seconds. So like the first time you put it, like this could have been a really temporary glitch. We'll try it again in a second. No, it's still broken. Try it again in 5. Try it again in 30, 60, whatever, right?
It's like feeding a baby. Wait 5 minutes.
Yeah, try again. Question, yep.
The service waiting the 30 seconds and putting it back on?
Depending on the infrastructure. So some of the infrastructure you can say, enqueue this message, but not until this time. And the infrastructure will go, yes, cool, and it will just kind of keep it there. Some infrastructure doesn't like that, so your service would hold it in memory, which where you're getting at is, what if your service crashes, you've lost your messages. Yeah, so it does depend on the infrastructure. Pick the one for the job. So that's what we call a back-off strategy, okay? There's a bunch of implementation in there, but essentially it's like, we don't want to immediately re-queue stuff because of transient failures, because transient failures tend to stick around a little while. Todd.
I mean, you've done a lot more of this stuff than me, but any of the like queuing systems that you've used actually does this out of the box properly? Because my experience is they never do this.
No. So the back-off strategy, no. And this is kind of my kind of second to last slide is, here's all the stuff you're going to need to build. Yeah. Bear with me.
Jitter.
Sorry?
And
jitter.
You don't get a broadcast storm and smash the crap out of your own server.
Yes. But as a concept, you don't want to re-enqueue everything straight away. You want to have a back-off strategy. The next concept you need to know is something called a poison message. Now, sometimes those failures are a transient thing. The third-party integrator that goes down, 1 in 10 requests. And they exist. And like just a simple back-off is really easy for them because 5 seconds later they'll be good. Sometimes the failure is your own fault. So whether that's bugs in your handler, some other piece of downtime, some message payload you weren't expecting, who loves null values, that kind of thing. Those messages are always going to go bang, yeah? And so what happens is, if we just go with a naive strategy of just sticking them back on the queue all the time, eventually your queue is just going to be full of what we call poison messages, okay? So they're messages that will poison your system. And they will stop the one good one from getting, particularly if you're re-queuing at the head of the queue, eventually you're going to have your good ones that potentially could work, are never going to get through because we've just clogged it up with, somebody implemented a new message contract and didn't tell us, and all of a sudden we've got a value that we weren't expecting, and it's blowing up. So if we keep re-queuing stuff, our failing messages will clog this system and just kind of either just waste CPU or actually stop good stuff from happening. So we call that a poison message. So I did this one. This is my design skills right there. So there's another concept that we call a dead letter queue. Some people call it a dead letter office, dead letter queue. And basically it's a queue that like no one's listening to, and it's just like a storage. So you go, this message has failed 5 times. So most message brokers, you've got the message payload, which is your JSON encoded whatever, or however encoded whatever. And they have some metadata properties on the message as well. So a really good use there is you have a property on that message that says this has been processed 1 time, 3 times, whatever. And you have some rules that says, look, if this has failed 5 times and our backoff strategy hasn't worked, stuff's just broken, put it on the dead letter queue, raise an alarm, that's an alert in New Relic or Seek wherever you like. Yep.
So like a cancellation token that sort of prevents like a denial service attack from commencing or something.
Kind of like that, but not. Yes, it's a way of preventing you from DOSing your own app just by trying to completely retry messages that are never going to work. But it's like, you imagine you've got a little shoebox on your desk and you go, I'm not dealing with that one, it can go in the box. And then, you might look at your logs and look at your application and go, oh, there's a new message type. And now all those things can work again. And if those messages were ones that, it mattered that we processed them, you can then take them from there, re-queue them, and then your thing should pick up from where it left off. Absolutely. Yes, in everything. Yeah, like you cannot do this without alerting and good logging and good instrumentation and observability. The days of building microservices where you have to SSH into 10 servers and grep logs, I know people have tried. You need good instrumentation. You need good alerting to say, hey, this is blowing up, raise an alarm, because that's an outage at that point. But that's the concept of a dead letter queue. If you've got too many poison messages, you want to get them out of your path. But don't lose them, because you might need. Like if it was a cache that is completely transient, cool, you can lose them, it doesn't matter. But using queuing infrastructure, you can create a queue just to store these things that you can go back and interrogate them later if you need to. All right, I have two more on this bit. So idempotency, and again, this is it depends. You need to think about idempotency. So particularly if you are retrying messages, messages might come out of order. You can't be sure that you'll get the new order before the payment. You can't be sure that you won't get the new order twice. You need to think about idempotency. So when you do something, like if you are inserting into a database, do a check that it doesn't exist first, that kind of thing. You need to think about idempotency. And again, that could be weeks of discussion, hypotheticals, but it's something you need to think about.
I'm really sorry. Can you define idempotency?
Sorry, yes.
I've never heard that word before.
Oh, really? Okay, cool. Sorry. So the question was, can I define idempotency? Which I feel like is a test, but no, I can. So it's basically, now I'm on the spot, I'm going to get this wrong. It's basically saying that you want to account for the fact that you could call something twice and kind of get the same result, not ruin the result. So like a really good example is if you're inserting a new customer, right? You want to make sure that if you call that twice, you don't end up with the same customer in your system twice. Yeah. So go insert it and go, it already exists, update it, or ignore it. Yep. Now everyone's going to argue with my. Yeah. I just saw from here. The view was amazing. The pitchforks came out. Go. You're next, Todd.
I was just going to say multiple actions, a single effect.
There you go. Multiple actions, a single effect. Excellent.
I wasn't going to disagree with your explanation. I was just going to say that you don't want to send someone $10,000 twice.
Exactly.
You don't
Yeah.
want to send them $1,000 of stuff on Amazon twice.
Yes.
It's that kind of.
So essentially, Essentially, when we're building this, we want to code defensively so that,
Yeah, the mathematical version is given the same inputs, you have the exact same outputs. every
Right,
time.
yeah. So you don't want two of the same customer. Had me worried for a minute. It was just like, you got one wrong. And the other thing you need to worry about, and this is kind of related, you need to be a little bit defensive about stuff not arriving in the order you expect, particularly where you've got different subscriptions. You expect that you'll get the new order event before the payment. Every now and then you don't. So if you're storing that saga, you want to go, there's a payment for an order we don't have yet. Let's create a blank order record for it anyway, because it's bound to come. There is a joke about async messages, and I can't remember it. Stuff can happen out of order. All right.
We had milliseconds.
Yeah, milliseconds.
Two servers
Yep.
came back in milliseconds.
Yep.
Because of machine names.
Clocks get out. Yeah, absolutely.
It totally threw us for like ages and put like a 3 second delay on it.
Look, thread.sleep is the cure to everything, especially UI testing. Dave.
I was going to say the other nice way is you can always go, well, put this message back on the queue and I'll check it.
And check it later. So Dave has a really good point. If you get something and you're not expecting it because you haven't seen the first one, consider it a message that you want to re-queue and give it a 5-second delay on the queue. Yeah.
Prime numbers for delays.
Yeah, yeah. I like the exponential one. It's good, like particularly dealing with integration stuff. It's like if this is out for 1 second, then check in 5, and then, you know. It's something you need to deal with. All right, I will get wrapped up pretty quickly. Some other practical considerations, and here I'm going to speed run and scare everybody. When you look at the sort of hello world documentation and code samples for something like Azure Service Bus, you go connect to the queue, they go like create a connection to the broker, connect to this queue, subscribe to it, and then just sit in a wait state, and then when this happens, kind of run this 3 lines of code. Now that's not how you want to write your applications. There's a bunch of practical considerations you need to think about. Connection management, because connections drop out. They just do. The network is not infallible. Queue and topic management. Again, so, you know, I talked about these handlers kind of registering based on their configuration and naming convention, stuff like that. So you're going to need to write code that goes, oh, I want this to be a multicast event of this thing. Therefore, my naming convention is going to be this. I need to create a subscription with this name. I've seen people try to, we do a deployment and then we jump onto RabbitMQ and go and manually create all the topics and subscriptions. It's not a fun time because you are guaranteed to forget one or typo it or whatever. Again, I saw an instance last week where Azure Service Bus was being a bit funky and we couldn't kind of refresh the queues because it was all just hard-coded into the thing and it was all a bit of a mess. So yeah, queue and topic management, creating them, naming them, all of that kind of stuff. You don't want to be doing it manually. So you want to automate that. Handler discovery and dispatching. So again, we've got this message of this type, go load this code from our, you know, IRC container or whatever, like go and find the function to handle this message. Again, you don't want to be sitting there with a bunch of spin logs going, oh, this happened, run this bit of code. You want to have something that kind of goes, here's a message, where's the code that needs to do it, and just kind of have a function that you can call. Yeah, the retries and error handling. Somebody said, yeah, no one does this well. It's baked into the infrastructure, but you need to write the code to decide when to retry it, how to handle your errors, that kind of stuff. And the other one was correlation logging. So distributed transactions, if you've got a message come through over here, that transaction ID or that order ID or that whatever ID, you put a GUID on it, you want to be able to trace in your log, whether you're using Seek or just use Seek. I realized as soon as I saw you shaking your head, I'm like, let's get into that one later. You know, you need to have tracing, telemetry, logging to do that. If I stop being facetious, you need to have what we call high cardinality identifiers. So like a GUID for a transaction, and everything that touches that wants to log that ID out. So you'll attach that to every message, ambiently maybe, and you can track what messages trigger other. And so you can kind of look at my logs and see all the different servers and how they handled that particular order. That kind of stuff. So you need to kind of bake that into your implementation. So yeah, you can roll your own of all of that, or I suggest don't do that. Go out and find someone that's done it. Mass Transit, rock solid, has been around forever. And Service Bus, the same. Nimbus is also actually, so Nimbus is something that I wrote with a couple of colleagues many years ago, and it is resuscitated and works. It's been in production for a couple of years, but I haven't written the documentation. It's coming. So particularly if you're on Azure Service Bus and you're interested, come talk to me about it. Rebus is another one, particularly for Rabbit. I think it might do Azure Service Bus now. It's not dead yet. So all of those things around like handler dispatching and connection management and queue topology and all of that stuff, these things kind of have it all baked in, and it's something that you want to do rather than just getting the Azure Service Bus SDK and going start a connection, because you're going to buy yourself a bunch of pain.
We just switched to mass transit and it's solved.
Oh, it's great. It's great. I mean, those guys they've been doing it for a long, long time, and it's absolutely solid. There's a lot of smart stuff gone into that.
Is there a reason you didn't put RabbitMQ in there? Because you mentioned that a lot.
So RabbitMQ is the broker infrastructure. Yeah. So again, you can grab their driver client and have to do all of that. Or you can get mass transit and it sits on top of the driver. It's like using an ORM rather than like a SQL connection, yeah? So you got mass transit and you go, there's my Rabbit server, and it will handle all of that stuff for you and just let you just write the code. So you go in, this message comes in, run this function.
You put it to Rabbit for your local development and say point to Azure Service.
Yeah, you can do that as well. So with Nimbus, you can use Redis as a local thing. Completely non-persistent, in most circumstances, you would never put that in production. But if you want to be an Azure Service Bus, when you get to production, you can configure it to point at that. Todd?
One thing just to be wary of, I guess, is as you change the transport layer, you get like different behavior emerging.
They all have their own idiosyncrasies,
They
yes.
make their own idiosyncrasies up into this layer.
Yes. But like as does everything, like SQL Server versus Postgres, Azure, everything has some sharp edges. But yeah, so you use something like this. Cool. Nearly done. Shameless plug time. If this is something you want to learn more about, I run some workshops on it. Now I've run a 3-day really intensive kind of very interactive workshop on this a lot. 3 days talking about this stuff is exhausting for everybody. So I'm in the process of condensing that down to a 1-day one that's sort of less interactive, but more, here are the concepts, here's the code, go away, play with it, come back to me if you've got questions kind of thing. If this is something you or your company are interested in, it would be remiss of me not to mention it. Come and talk to me. I would love to chat. So yes, if this is something that you would like and you want some training, I've been doing it for a long time. We've done a lot of questions, but do we have any? I have time for some more, and I have the energy. Yes.
Do you have anything to say about message versioning? And do you, I'm not really familiar with the sagas, but
Yep.
often the times where I'm having to work out how I would compensate an error.
Yep.
That seems like the panacea for that.
Yes, cool. So the question was, do I have thoughts on message versioning? Of course I do. And versioning sagas. Cool. Again, these are big topics. This is very general. So, message versioning, I've found when your events are very semantic, okay, so like we have a new customer, they tend to not change shape that much. They become additive. So we've added a new property to the customer rather than we've changed our definition of a customer. Okay, so very, very rare. It's one of those things that when you talk about messaging, everyone's like, oh my God, contract versioning is going to be the hardest problem ever. I've rarely had issues with it because at the point where your message changes substantially, it's probably because semantically it's different. And at that point, you just send 2 messages and you handle it while you deprecate the older feature. Where versioning does come in is like adding a property or taking one property and turning it into an array of things or whatever. And they're sort of fairly easy to compensate. Actually, if you've got one property and turn it into an array, just give it a different name. And then your handler will go, is this the one thing or is this the multiple things?
Document DBs enforce that thinking model.
Yeah, exactly. Document DBs kind of have taken away the schema. So don't be afraid of contract versioning. It tends to not be that difficult. And when you hit an issue with it, it should be pretty clear what the solution is. So that's the first one. Long-running Saga versioning is slightly trickier. But again, particularly if you're using, I'm going to tell a story. I worked on something that was like this, like long-running approval workflows with really flexible workflow steps. Some people in this room may have worked on it with me. No, they actually didn't. It was for a consulting company. And somebody high in that consulting company went, we are a consulting company around this particular vendor. This vendor has a workflow tool. You should use that. And we looked at that and went, serializing that's going to be really hard because the workflows are going to change and this serializes it as XML, which does not merge particularly nicely. We ain't going to do it. And we had a big fight. And the team building it won that fight, thankfully, because 6 months later, that workflow tool was deprecated and the thing that we built was still in production 10 years later. and I stand by that. So roll it yourself, like have a class that takes things and unit test it a lot. And if you do have the instance where you have to change your workflow at all, you can write a lot of tests around that and handle cases and stuff like that. Taking it all as a state and kind of trying to serialize that is really, really hard. But again, I think there was a question earlier, like, do you kind of store the events and replay the events to get the current state? And if it was a complex workflow, that's what I would do. Does that answer the question? Not quite. We can probably go deeper and be a bit more specific when the microphone's not on. but yeah, like in general, like if your state machine is really complex, don't serialize the whole object to database. Serialize the events as they came in, which is kind of event sourcing. Sorry? Like Git, yeah. Serialize the events that came in, and then when you rehydrate that saga, quickly rerun those events to go, okay, we're here. Because you can unit test that. Yep. Anyone else?
You gave the kind of classic example of credit card processing as something that might fail, so you
not might. Yes.
And I absolutely understand you can do that, and if you do that, it generally changes the user experience.
Yep.
But like lots of production systems don't want that user experience, and like you type the credit card number wrong, you want that feedback immediately. You don't want an email later to say I've typed it wrong. So how do you actually do that in the real world?
Yep.
Do you allow some sort of timeout to see the response immediately?
Yeah,
is there
I love the real world implication. But yeah, so sometimes they'll come back really quickly. Okay, so they'll go out and they'll come straight and go, your number's wrong or the date's invalid or whatever. But you can't rely on that. And so what happens if you assume it's always going to come back quickly, like your customer is calling your service, like your back end is then synchronously calling the thing. Now sometimes, like say you've got a 30-second timeout on your end, they might have a 32-second, they might take 32 seconds. So in the happy path, absolutely, it comes back, 100 milliseconds, this number's wrong, declined, whatever it is. And that's good, you can show it to your customer. If you assume that's going to happen, you're going to have the time where it takes 35 seconds, and you're just going to show your customer 500, right?
Completely willing to admit you shouldn't do it synchronously.
Yep.
How do
Cool.
you do it in the real world?
In the real world.
Async, but still show results.
Yep. So the easiest way is query the saga. Okay. So what you do is you've got, a record in a database that is kind of close to your customer, and it has status of that transaction. And you can poll that. Like you can do it with SignalR, or you can just sit there with a spinner that in the background is hitting the JavaScript API going, are we there yet? Are we there yet? Are we there yet? Are we there yet? And it'll come back and go, yes, it succeeded. Or no, it came back with this message. So how you build that is, again, you've got, customer hitting an API. That API is hitting a database table, which is transaction ID blah. It's in a pending state. You go call the payment gateway. Payment gateway hopefully comes back in 100 milliseconds, hits your webhook. You process that event, right? And then writes to your table, this transaction has succeeded. So within the space of one magic spinner facade, it's come back and gone, yep, we're good, yeah? Or if it doesn't work, it spins and it spins and it spins, and you can even say, this is taking a little longer than expected, and then it comes back and goes, no. And then so you can show that feedback. So the fact that you can show user feedback quickly sort of doesn't determine.
So you're essentially putting a synchronous facade on top of your asynchronous processing behind.
No, polling it basically. Like you're hitting an API that says, what's the status of this? What's the status of this? From the user's perspective, it's a JavaScript spinner. It's CSS.
So, the other one is there's defense in depth there, right? You talked about an invalid credit card. So the first step is, do I have a full 16 character?
Yeah. So you can do a lot of like client-side validation.
And then there are algorithms to validate, is this a valid? They have a CRC check, and most the different brands have different CRC checks. And so that's step 2. And you can do that in the UI.
Yeah.
And then it's go through, and then you can start the processing. It gets really scary in places like Japan, where a restaurant bill can be split 4 ways with 4 separate credit cards.
Not online, generally.
Maximize their points.
But yeah, you look at like Amazon, right? So Amazon will, if you
Always take the order.
will always take the order. Now they might email you back 15 minutes later that says, look, we tried to charge that card and it got declined because it's expired or insufficient funds or whatever. You've got 12 hours or 24 hours, 3 days to rectify it before we cancel your order. So they'll give the impression of, hey, this worked. And again, they'll do some validation to go, that is actually a credit card number. But at Amazon scale, they can't be waiting on payment gateways. They would take down the world's payment gateways. But yeah, so what I've done in that circumstance is you've got an API that will just return the status of that transaction of your storage of it, like your Saga storage of it. And it can get updated by payment gateway hitting your webhook, that's sending a message, an event, your front-facing service listening to that event and updating the database table. And that, in most cases, will happen in, half a second.
We just throw things into another queue, like as it goes through the process, and basically a notifier throws off to another service to say, oh, this happened, this happened, this happened. So wherever in the chain, so we have a problem where people are buying energy on the spot market, they could get a price, go get a coffee, come back, but that price is no longer valid. So it's got to automatically come back to our system, validate the price is still
It's still valid, yeah.
and either come back and say, no, it's no longer legit, or if they do purchase it, and it says, oh, I need to buy 10 units of what, it says, we've only got 5. We just go, here's 5, we cancel the other 5.
Yeah, and there's other tricks you can do, like to do stuff at scale, like if you're buying Taylor Swift tickets, you've got 2 minutes to complete this transaction. Sorry, and so you'll get an allocation. It's like you've got we've allocated. You want 3. We've given you the option to buy 3. If you don't get it within that, we'll kind of hand it back. There's tricks to do that stuff at scale, but yeah, in general, doing that async workflow will give you a more reliable outcome than waiting for it. I've been talking for an hour and a half. Is everyone tired?
A lot longer than that, just to us for an hour.
Anyone? Any other final questions?
So why does Microsoft keep bringing out new message queues?
That is the discussion for a whole other thing. Before I finish, you were around some of that. I have 2, and now here's where I'm going to need to move. I have 2 things. Do you have a writer license? Do you have a JetBrains? Have you used JetBrains Writer?
Yes.
Yes?
In my workplace.
Do you have a license for it?
Yes.
Would you like a license for it?
Okay.
You earned one. And do you have one? These are the 2 most interactive participants tonight. Do you have one? You have one? Next to Dave. Sorry, I've forgotten your name.
Oh, yeah, I have my own.
You have your own?
Who doesn't have
Who
one?
doesn't have one? Would you like a JetBrains license? There we go. Thank you to JetBrains. Yeah. JetBrains do, not only do they make really good dev tools, like this is not an endorsement. I paid for Writer with my own money. I've been using JetBrains tools for a long, long time, and I can't imagine writing code without them, to be honest. And they do an amazing amount for sponsoring user groups. And Turtle didn't make me say this. This is my own. They do a lot for sponsoring community groups. So, sorry?
Runs on Linux.
It runs on Linux, yeah. I use it on a Mac. This is, yeah. Which is your only decent option now on a Mac because Sharp Develop is finally dead. Only a few people remember that. I started on Sharp Develop, which became Mono Studio, Mono Develop, which became Xamarin Studio, which became Visual Studio for Mac. But that's a whole other saga.
That's another talk for another time. Thank you everyone for coming tonight. Big thank you for Damian for taking the time to put together the slides, and Lorraine for taking the time to put together the slides and present
Animating
tonight.
them. Animating them.